This video is going to talk about why divergence is the mathematical operator that gives us how much flows out of a region of space. So divergence is a vector operator. It takes a vector field and turns it into a scalar field. It gives us where the sources and where the sinks are, and it quantifies how much flows out of a region of space or how much flows into a region of space. Now, to give you an example, we're going to use what's called the continuity equation. I'm going to specifically write the continuity equation for charge conservation. So what we have is d rho dt, so the time derivative of, in this case, our charge density, plus the divergence of J, which is our current density, is equal to 0. Now, this continuity equation is not just used in E&M. You can think of it as a mass flow equation in fluid dynamics, where this is the density of your actual fluid, and this is the fluid flow. You can think of it as how heat will flow. Heat also flows as a result of gradients, particle flow in a gas. This continuity equation is actually really, really powerful and deep, and this derivation will work for any of them. But mostly what we're focusing on is why is the divergence going to be what flows out? And we're going to talk about this a lot in electricity and magnetism. Charge is conserved. That means charge can't be created or destroyed. So if we have charge in a particular region of space, we've got our starting charge, and we're going to have our ending charge. In order for those to change, you must have some charge flowing in and some charge flowing out. So not only can charge not be created or destroyed, but charge can't teleport from here over to here without going through the intervening space. Charge is locally conserved, which means that if you put a region of space, a box that contains some charge, the total amount of charge inside that box has to stay the same unless some current flows out. Current, specifically, is flowing charge. So we can say that I, which is our current, is equal to dq dt. Now, more specifically, we're going to talk about our area current density, J, and J is defined as the derivative of I with respect to the perpendicular area. So when we have current flowing, we're going to have a certain current density. Now, if the current is flowing uniformly across that cross-sectional area, what we can say is that I is equal to J dotted with that area vector. Given that we have this idea of local charge conservation, what we can do is we can define our region of space to be a box. And this box is going to be of length dx, of width dy, and of height dz. Standard little infinitesimal cube. And what we can say is that because we have current defined as JA, and if they're perpendicular, of course, it's just the magnitude of J times the magnitude of A, we can say that there's going to be a certain current flowing in the x direction, a certain current flowing in the y direction, a certain current flowing in the z direction. We're going to start with just the x direction. So Ix will equal whatever Jx we have evaluated at one end of our box, which we'll go ahead and say is x plus delta x. And of course, it's also going to be y naught, z naught, and so forth, minus jx evaluated at x. Okay? So we have the current flowing in minus the current flowing out. All right, well, what's our cross-sectional area? Well, a cross-sectional area for that box is going to wind up being delta y, delta z. Well, this reminds us of something. What we could do is we've got this j of x plus delta x minus j of x, and this looks kind of familiar, and it might look even more familiar if we were to divide this by delta x. But of course, if we divide by delta x here, we have to multiply by delta x right there. Now, this should really be reminding you of something from a class you've taken before, but let's make it even more explicit, and we'll say we'll take the limit as delta x gets smaller and smaller. And of course, this has now become a derivative. Specifically, since j is a function of x and y and z, although I suppress the y and z, what we've just done is we've taken the partial derivative of j with respect to x. So this is equal to the partial derivative of j with respect to x. And this is times delta y, delta z, delta x. Okay, well that's kind of convenient. And we could do the exact same thing we just did here to figure out our I sub y. So I sub y will wind up being dj dy, also delta y, delta z, delta x. And of course, Iz will be the partial with respect to z, delta y, delta x, delta z. Well, that's awfully convenient. What we can now say is that Ix plus Iy plus Iz is equal to the partial of j with respect to x plus the partial of j with respect to y plus the partial of j with respect to z, all times delta x, delta y, delta z. Well, Ix plus Iy plus Iz, that's just going to be equal to our I out minus our I in. It's whatever current we have flowing out minus the current we have going in, and we can just call this the net current. Now, our net current, we had said previously, was the derivative of charge, the time derivative of charge specifically. So what we can say is that the amount of current flowing out of our box, out of our region of space, is going to be the divergence of j, and that's going to have something to do with the current that's flowing out of our box. This is the first hint we have that this divergence is actually the mathematical operator that tells us how much stuff is flowing out, which is why it's called a divergence. It diverges out. So when we have the divergence of j times that volume element, this is equal to I net. But I net is also equal to minus dq dt. Well, if minus dq dt is going to be equal to this, well, we could move this over to the other side. So we now have 1 divided by delta x, delta y, delta z. There's a minus dq dt is equal to the divergence of j. What we can do is we can say that for sufficiently small delta q, delta y, and delta z, we can pass this inside of our time derivative as long as it's not changing with time, and then q becomes rho, our charge density. So we have minus d rho dt is equal to the divergence of j, which written in a more familiar form is d rho dt plus the divergence of j is equal to 0. The charge density that we have changes with time, and the way that it changes with time is our current density flows out or flows in. So there's a relationship. The total charge must go down when j flows out. The total charge must go up when j flows in. Outflowing j would be a positive j, making this negative. Inflowing j would be negative j, making this positive in order for it to balance out to 0.
This video showed why the divergence is the mathematical operator that gives how much a vector field flows in or out of a region of space. The divergence is a differential operator and turns a vector field into a scalar field. In this particular example, the only way for charge to move in or out of our region of space is through the surface. Charge can't teleport, and net charge can't be created or destroyed. Divergence, acting on the current density, shows how the charge density changes with time.